Hello students, and welcome to today's lecture on mechanical creep. Due to the pandemic at hand, this will be your final lecture for manufacturing systems and materials technology. As always, if you have any questions about this lecture, please feel free to email me using the email address on this slide. The original plan for this course was for me to deliver 8 lectures and a 2-hour revision session for your final examination. Due to the time constraints and needing to conclude teaching before the Easter holiday, we will not be covering the topics of wear and selection of materials for engineering applications. However, based on what you've learned already through this course, you should know how to select appropriate materials for different applications. We will also only be covering an abridged version of creep, where I will be covering the basic topics needed for your final examination and your careers as engineers. As such, we only have 3 teaching objectives for today's lecture. The first is to explore time-dependent behavior and physical mechanisms of creep. The next is to predict creep of structures. And the third and final objective is to demonstrate an understanding of the role creep plays in design. In our first lecture, we discovered systems can fail mechanically in 2 different manners, through permanent deformation and fracture. In our previous 2 lectures, we discussed how failure by fracture can occur. If only one load is applied to the object, use the equations that we learned in fracture mechanics. And if multiple loads are applied to the object, you use the equations that we derived in fatigue crack growth. Under deformation failure, we discussed how when multiple loads are applied to an object, the material can fail through fatigue. And there were 2 types of fatigue that we talked about that had to do with deformation-based failure. The first was stress-based fatigue, which tends to occur at higher number of loads, and the second was strain-based fatigue, which tends to occur at lower number of loads. If failure by deformation happens when only a single load is applied to the object, it can either be time independent, in which case we use the equations that we learned in elastic failure, or it can be time dependent, in which case we use the equations we're going to learn through mechanical creep. Creep is the permanent deformation of a material that occurs gradually with time under a persistent mechanical stress. Like strain-based fatigue, it is often more important to engineering designs that involve high temperatures, such as steam turbines in power plants, jet and rocket engines, and nuclear reactors. But creep can also occur at low temperatures, such as the slow, gradual loosening of plastic eyeglass frames and the movement of ice in glaciers. In the picture on the right, you can see another example of creep that occurs at a low temperature. This cardboard box has had another box stacked upon it for a long period of time, where it has been stored at ambient room temperature. When the top box is removed, you can see that the bottom box is permanently deformed. In metals and crystalline ceramics, creep deformation generally only becomes large enough to be important at temperatures between 30 and 60% of the melting temperature, T sub m. However, like I said before, this is only a general rule of thumb because creep can occur at lower temperatures as well. In some polymer materials, creep becomes a problem when the temperature exceeds the glass transition temperature T sub G. And the glass transition temperature is the point at which a polymer stops acting like a brittle, hard material and starts acting like a ductile, stretchy material. What's important to also remember for the point of creep is that all temperatures are always defined in Kelvin for the equations. So if you're given the temperature in Fahrenheit or Celsius, you do need to convert before you can utilize these equations. There are 2 mechanical models that can be used to describe the relationship between force and displacement in creep. The first, or the steady state creep model, assumes any deformations undergone by the system are permanent. Here, the component can be modeled as a dashpot damper system, where force and velocity are proportional to one another and related by a constant c. If we look at the graph in the center top of your slide, we can see how displacement relates to time as a force is applied to it. And the graph in the top right describes how force is related to displacement. On both graphs, there are 5 time points, 0 representing your starting time point, 1, 2, 3, and 4 representing your final time point. Between time points 0 and 1, a instantaneous force, P, is applied to your system. Initially, there are no deformations that are occurring because the dashpot is preventing the system from moving. However, between points 1 and 2, where force is held constant at P, there is some displacements that are occurring, and it's a linear increase in displacement. The slope of this linear relationship is given by M, which is defined as P, the load, divided by C, the constant. At time point 3, the load is instantaneously removed from the object, and displacement remains constant for an infinite amount of time afterwards because it is permanent deformation, and there's nothing to cause the system to contract again and for deformation to return back to what it was. The second model is transient creep, and it assumes that the deformations undergone by the system are elastic or recoverable, and the rate at which the deformations are recoverable is a function of time. This can also be modeled by using a dashpot damper, but you also need a spring to be in parallel with it. If only a short amount of time has passed, little to no deformation is after the load is removed, then little to no deformation is recovered. But if an infinite amount of time has passed, all deformations will be recovered. Here, the maximum rate at which displacement can increase with respect to time is limited by the ratio of force P to the dashpot constant C. And the maximum displacement that can occur is if the force is applied for an infinite amount of time is the force P divided by the spring constant K. You may have noticed from these deformation models that they don't take into account initial elastic deformation that can occur to an object when a force is applied. And as you can imagine, when you're thinking about the relationship between stress and strain, this initial elastic deformation is important. You can account for this initial elastic deformation by adding a spring in series with either just the dashpot in the steady state creep model or the dashpot and the damper that are the dashpot damper and the spring, which are in parallel with one another in the transient creep model. So in these models, since we're looking at stress and strain, we have normalized force for cross-sectional area, and we are now applying a stress instead of a force to the object, and we are measuring displacement in terms of strain, or displacement normalized by initial length. Similar to before, you have some type of initial load or stress in the situation which is applied to the object at time point 1, but in the steady state creep model and in the transient creep model, this leads to initial elastic deformation of the component. And the magnitude of this deformation is the stress divided by E sub 1, where E sub 1 is the constant for that spring that we've added into the system. Then pretty much everything is the same from before. If you were to look at strain with respect for time, with the exception that when the load is removed from time point 2 to 3, that elastic deformation is recovered in the object. If you look at the stress versus strain instead of the force versus displacement graphs on the right, you will see what you would expect given our knowledge of the relationship between stress and strain in materials. Between time point 0 and 1, when the stress is applied to the object, the stress increases to its load, and there is some initial elastic deformation, which leads to an elastic strain. And then you have some type of permanent strain which is occurring, or plastic strain which is occurring. And in the steady state creep model, we say strain sub SC for steady state creep, and in the transient creep model, it's strain sub Tc for transient creep. Again, when the load is removed, or when the stress is removed, then the stresses drop down to 0, and in the steady state creep model, no strains are recovered beyond those of the elastic strain. And in the transient creep model, if you gave it an infinite amount of time, all the strains would be recovered. In a lab, the most common way of testing for creep is to apply a constant axial, tensile, or compressive load to a bar or a cylinder for a long period of time. Strain is then measured over this time from the point of initial application to the time of rupture. A typical graph showing the relationship between strain and time is shown on the right. The strain time curve is typically broken into 3 stages, where the stages are defined by the changes in strain rate. Now, strain rate, if you remember, is the change in width of strain with respect to time, and the formula for it is given in the bottom left-hand corner of your slide. During this primary stage of the strain time curve, transient creep is occurring when a force or stress is instantaneously applied to the object. This leads to instantaneous elastic and/or elastic and plastic strain, which is represented by that horizontal dotted line. Due to the nearly instantaneous deformations, the strain rate, or change of strain with respect to time, is extremely high at this point. As time progresses, strain accumulates through transient creep, and the strain rate gradually decreases until it approaches a constant slope, at which point stage 1 ends. The secondary stage is defined by steady state creep and is the longest of the 3 stages. During the second stage, the strain rate remains relatively constant and the material continues to deform. Eventually, the strain rate begins to increase, marking the end of the secondary stage and the beginning of the tertiary stage, in which case unstable strain accumulates throughout the object until it ruptures at the time of rupture, T sub r. The reason why there is a dramatic increase in strain rate during this tertiary stage is that large levels of plastic deformation have occurred, and as a result, the cross-sectional area of the test specimen has significantly decreased. As force remains constant, the stress then increases dramatically during this stage. A number of empirical equations have been proposed to describe the time-dependent behavior of creep strain, epsilon sub c. One is shown here, where A, beta, and gamma are constants. You do not need to worry about these equations for the test, but you should be aware that equations like these exist. The 4 quantities most commonly used to summarize data from creep experiments are stress, temperature, steady state, creep rate, and time to rupture. If you remember, steady state creep rate is the slope of the strain time graph in the secondary stage of creep. As creep is affected by factors such as stress, temperature, and humidity, creep tests are generally performed and reported for a large range of these parameters. You can then use this information to create the relevant graphs you need, such as the strain time and stress strain graphs seen here, to get the data you need for your applications. In the 4 graphs at the right, you can see the transient and steady state creep response of an object to a series of stresses. As you would expect, higher stresses yield higher strains for a given time point. In graph B, the stresses and strains at time points 1, 2, and 3 are used to create stress-strain plots where each curve represents a different time. In graph C, those curves are used to estimate the secant modulus, E sub c, where the slope of this line is going from the origin of the graph to a given point on the stress-strain curve. Here, the point on the stress-strain curve used to calculate the secant modulus is defined by a strain value epsilon prime. Finally, in graph D, you can see how the secant modulus for a given strain changes with respect to time. As with fatigue, creep is a time-dependent phenomenon, and the factor of safety is not a deterministic value, but changes depending on when it's being investigated. From experiments, we can create a failure curve where stress is a function of time to rupture, T sub r, and temperature. The curve on the graph on the left shows this failure curve for a given operating temperature, big T hat. Consider now a combination of stress and time, which are your operating stress and time for a component being analyzed, and they are defined as sigma hat and little t hat. To prevent failure from occurring, this point must lie on or below the blue curve. If it lies above the curve, then failure will occur. Now consider a point on the curve, 1, which is the failure stress sigma sub 1 that corresponds to your operating time T. The ratio of sigma 1 to your operating stress sigma hat gives you a factor of safety, which is defined in the bottom left-hand corner of the slide. While useful to define your factor of safety in terms of stress, you may also want to define it in terms of operating time. To do that, you take the point on your failure curve 2, which is your time time to failure that's associated with the operating stress. If you take the ratio, and that's depicted as little t sub r2. The ratio of little t sub r2 to t hat, or your operating time, gives you a factor of safety with respect to time. Generally, because creep, like fatigue, can be difficult to predict and or can have a wide range of error associated with it, you're going to want a safety factor of at least 1.5 whenever you're designing a component where creep is something you need to consider. Also of interest here is the safety margin in terms of temperature. So we can define the safety margin delta T sub f, which is the difference between your failure curve, which is that solid blue line in the graph on the right, and the failure curve that would correspond to your operating stress and your operating time, sigma hat, little t hat. The difference between the temperature for this dotted failure curve and the operating temperature for the solid line curve is delta T. Here we're going to go over an example to help you understand how you can apply some of this data from creep experiments. So we have a solid cylinder rod with a length of 0.1 meters, and it's clamped horizontally at one end, and the other free end is subjected to a vertical load of 25 newtons. So it is a cantilever beam. The rod is made of acetyl copolymer, and the temperature of application is 20 degrees Celsius. The design requires that the strain in the rod due to creep must be less than 2% in 1 year. So what would the maximum deflection be at 1 year to prevent within these design criteria? To solve this problem, we're going to first plot a 1-year isochronal stress strain curve for acetyl. Then we're going to determine the allowable stress for a 2% strain limit. Third, we're going to determine a suitable diameter for the rod for a limiting strain of 2% in 1 year. And then we can finally determine the maximum deflection in 1 year. So on the left, we have a graph showing the results from a series of experiments where acetyl is loaded at a constant stress for a constant amount of time. Note that relatively little deformation occurs at the beginning of the experiment, but as time progresses, the strain rate increases. As such, time is plotted on the logarithmic scale. If we calculate the percent of stress at 1 year for each of those curves, we can create an isochronal stress strain curve like the one shown on the right. From the stress strain curve, we can determine that the maximum stress that the acetyl can experience at 2% strain is 17 megapascals. Next, we have to determine the diameter D that will withstand a 17 megapascal stress. So the formula for stresses in a cantilever beam is that stress is equal to m times y divided by I, where m is the moment, y is the distance from the neutral axis, and I is the second moment area. We know from the previous slide that the maximum stress that the beam can undergo is 17 megapascals. We know that the moment is 25 newtons, or the load being applied, times the length of the beam, which is 0.15 meters. We know that the maximum stresses occur the furthest away from the neutral axis that you can get. And so this Y max value is d divided by 2, or the diameter divided by 2. And finally, we know that the second moment area is defined by this quantity in the third line on the right. If we put those all together, what we find out is that the minimum diameter that the rod must be is 13.1 millimeters. Finally, let's look at what the maximum deflection in the beam is. And we know that deflection in a beam at the free end of a beam is defined by this equation over here, where delta max is equivalent to PL cubed divided by 3EI, where P is the load, L is the length of the beam, E is Young's modulus, and I is the second moment area. And we know we know P, we know L, we know I, all from either the information given or the previous, what we found out previously in the problems. What we're missing is E, this Young's modulus. And because it's creep, we're not using the Young's modulus itself, but we're using E sub s, or the secant modulus. And so the secant modulus at the time point we're looking at, which is when 2% strain occurs, is the slope from the origin to this point over here, which is 2% strain, 17 megapascals, and that gives us a secant modulus value of 850 megapascals. The maximum deflection that will occur in the beam is therefore 22.9 millimeters, so nearly 23 millimeters. The physical mechanisms causing creep differ between the classes of materials being examined. Even within a material, the mechanism that causes creep can change with both stress and temperature. Viscous creep is based on the idea that some nominally solid materials behave in a manner similar to a liquid with very high viscosities. And this is generally true for some amorphous solids such as silica glass or some polymers. In response to an applied stress, atoms or molecules in a material, or groups of molecules, move relative to one another in a time-dependent manner, resulting in creep deformation occurring. Creep through viscous flow occurs via two main mechanisms, either diffusion or dislocation. In crystalline structures, both of these mechanisms involve the migration of crystalline defects. In general, diffusion creep involves atomic vacancies, or empty atomic sites in the crystal lattices moving within or along the grain boundaries, and it's more dominant at lower temperatures. Dislocation creep, which is more dominant at higher temperatures, involves the motion of dislocations along the slip plane. Increases in temperature increases the oscillation or the movement of atoms around their equilibrium positions, which increase the likelihood that they're going to move and creep is going to occur. This is the reason why at higher temperatures creep occurs more than at lower temperatures. We know from our worked out example and the mechanics of creep that both stress and temperature can cause variation in creep deformation. When conducting experiments, researchers conduct a number of tests in which both stress or temperature is held constant and varied between greater and lesser values. And you can then produce graphs similar to the one over here where temperature is held constant but stress is varied. But what if we wanted to know how much creep deformation would occur at a stress or temperature that's either between or outside the values used in the experiments? Such a predictive equation would be useful for design and failure analysis purposes. From experimental analyses, we know that creep deformation is positively correlated with stress and temperature. So higher stresses, higher temperature cause more creep. We also know that when temperature is held constant, the steady state strain rate, which occurs during the secondary stage of creep, is related to the applied stress with the power law. The simplest mathematical model to describe the relationship is presented here on the slide, where the creep exponent, n, usually lies between 3 and 8, and both the constants b and n can be determined experimentally. Similarly, from experiments where temperature is varied and stress is held constant, the steady state strain rate was found to be negatively correlated with the inverse of the absolute temperature measured in kelvins, meaning higher strain rates occur at higher temperatures and lower strain rates occur at lower temperatures. This makes sense based on what we talked about previously. The slope of the relationship between the strain rate and the inverse of temperature is equal to the negative activation energy for creep, Q, divided by the universal gas constant, R. The expression relating the strain rate to temperature is given on this slide over here, where C is a constant. You can take these two equations for strain rate at a constant stress and strain rate at a constant temperature to create a generalized equation that accounts for both changes in stress and changes in temperature. This combined creep equation is given in the center of the slide, and you will notice the equation depends on three constants here, A, N, and Q. All these constants need to be determined experimentally. This generalized equation is powerful as it can estimate steady state creep at a variety of stresses and temperatures. It can also be used to estimate the strain rate at a unique stress, temperature, or combination of stresses and temperatures that haven't been determined experimentally. These generalized equations that we just learned are useful when predicting when a component will fail due to creep deformation, which can be important during the design of materials and components. And as we stated in the beginning, it tends to be more important at higher temperatures and less important at lower temperatures. But as we can see in these two examples, and we'll go over, just because it's low temperature doesn't mean creep won't occur. In the example on the left, you're seeing a pipe that has burst due to creep because it has been operating with a pressurized fluid within it that is a high temperature for a prolonged period of time. Over the years, the combination of high pressure creates high stress, and the high pressure creating high stress and the high temperature can cause creep deformation to occur, ultimately leading to the pipe bursting. In the figure on the right, we see creep deformation occurring in lead pipes, which these lead drainage pipes used to be very common in older Victorian houses in England. When they were put up on the wall, the pipes were initially straight and drainage wouldn't be a problem. But over time, the pipes would eventually sag, and this could lead to the drainage pipes not working anymore because they have these little bends in them and these pockets in which water and other fluids can accumulate. When using the aforementioned general equations on the previous slides, a good rule of thumb is to ensure that the test data used to determine your coefficients extends to 10% of the service life of your component. So that means that if you have a component that you want to last for 25 years, your longest experiment should be at least 2.5 years long. In addition, the ranges of stresses used in your experiments should encompass the stress value you want to use for the service life of your material. And if this is not possible, that stress value for the service life of the service of your material should be close to the stress range that you use. So if you want a pipe to operate at a stress of 50 megapascals, you should have a range of stresses in your experiments that encompass 50 megapascals. So in this example, we are going to be looking at applying these equations that we've learned. So a steel component operates at a constant stress of 150 megapascals at 450 degrees Celsius. Creep tests for the steel are performed at 450 degrees Celsius and give a strain rate of 8 times 10 to the negative 10th with units of 1 per hour and at 21 megapascals. The creep test for the steel at 450 degrees Celsius gives a strain rate of 8 times 10 to the negative 10th at 21 megapascals and 4 times 10 to the negative 9th at 30 megapascals. And we have 3 parts to this question. First, if the strain for the component is limited to less than 1% in 2 years, will this component fail? 2, if the component is initially 4 meters long, how long will it be after this 2-year period? And 3, what is the factor of safety for this 2-year period? Based on what we learned on the previous slide, you might notice that this test data that we have will not be good for testing the lifetime of this component. The values for the constants that we will get will not be appropriate to use here, but we're just going to use this as an example. So for this first part of the problem, we want to work out the strain rate that occurs under this stress. Looking at our previous equations, we have 3, 2 of which are dependent on temperature, and 1 of which is not. We're going to take this last one because the experiments will run at a constant temperature and our component is going to be operating at a constant temperature. So the steady state strain rate is going to be equal to a constant B times the stress raised to a constant N power. We have, from our experiments, 2 sets of strain rates and stresses, and we're going to plug those into this equation to get 2 equations with 2 unknowns. If you'll notice, we're defining time in the units of 1 per hour instead of 1 per second, and we're defining stress in terms of megapascals instead of pascals. Now this is fine because this just means that our constants B and N will be defined by these units of hours and megapascals instead of seconds and pascals. This also means that anytime we use these constants, we have to input our stress and our strain rate in that manner. So with these 2 equations that we have, the first thing we're going to do is solve for B, and then we're going to set B equal to B from equation 1 and 2, and we get what's in line 4, which is 8 times 10 to the negative 10th divided by 21 raised to the n power is equal to 4 times 10 to the negative 9th divided by 30 to the nth power. We rearrange that, we can solve for n. We find that n has a value of 4.51. We can then take either of the first 2 equations to solve for B. Took the second one here, so B equals 4 times 10 to the negative 9th divided by 30 to the 4.51 power, which gives us a value of 8.65 times 10 to the negative 16th. So now that we have both of our constants, we can solve for our strain rate at 150 megapascals, and we get a strain rate of 5.7 times 10 to the negative 6th. To figure out the total strain that we will have after 2 years, all we need to do is multiply our strain rate times time, because strain rate is strain divided by time. The value we're going to use for time is 2 years in terms of hours and not seconds, because of what we talked about before. So the total strain after 2 years is equal to the steady state strain rate times time, or 5.7 times 10 to the negative 6 times 2 times 365 times 24, and that gives us a strain of 9.99%. So the pipe will absolutely fail because we set our failure value at 1% strain. An interesting thought experiment would just be to think about how we could avoid failure in this scenario. And one simple way would be to decrease the operating temperature to a level at which of which creep deformation is minimized and no longer becomes important or is less than our design criteria for failure. Another way would be to decrease the stress, and this could be done either by changing the geometrical design of the component, or the material the component is made out of, or the force that's applied to the component. For the second part of this problem, we need to determine the final length of the bar. And we know that the final length is equal to the initial length plus the change in length. So L sub f equals L sub naught plus delta L. We know the initial length from the problem is 4 meters. What we don't know is the change in length, but we can determine that using the equation for strain, where strain is change in length divided by initial length. So if we rearrange that, we find that the change in length is strain times initial length. Plug that into our equation, and what we find is that the final length is 4.4 meters. So this bar has extended about 400 millimeters over a 2-year period, and so that's quite a lot of deformation to occur. Finally, since we know this bar is failing, we don't actually really care about the factor of safety. It is too low, but we'll calculate it for academic purposes. And we know that because it's failing, the factor of safety should be less than 1. So we're going to use the factor of safety equation, which uses stresses, which has our stress at failure, which sigma 1 divided by our operating stress, sigma hat. From the problem we have that sigma hat is 150 megapascals, and we need to calculate sigma 1. And we can do that using our steady state strain rate equation. So steady state strain rate is equal to the final strain divided by time, and it's also equal to the constant V times stress raised to the constant N power. So taking that information, we can rearrange the equation and solve for sigma sub 1, and then input that into our factor of safety equation, which is what we have the next line. And so the factor of safety is equal to the quantity, the final strain divided by B times time, all raised to the 1 over N power divided by sigma hat. Our final strain, we're using the value of 0.01 because that's what we're designing towards, is 1% strain. Again, time is 2 years, and sigma hat is 150, and the constants are from part A. When we do this, we get a factor of safety of 0.6. So, like I said, less than 1, it's going to fail, but it's just good to know how to use these equations. To get you to work with these equations a little more, I'm just giving you some home examples here. You can read through them and try them on your own. The first 3 parts have the answers in red, and the last part does not. So if I were you, I would just go ahead and pause the slide, copy down this information, or find out what equations, and just try to get these answers on your own. So that's all we need to learn about strain. And so I just wanted to go, or creep, sorry. So I just wanted to go over a bit about what will be in your final exam. Like we've gone over during class, half of your exam will be on what I've taught you with failure analysis, and half will be what on the topics Jeff Goss has taught you. All the topics that Swerve has taught you were put into your semester project. Just to review, the main topics that I have covered in this lecture are elastic failure, fatigue, creep, and fracture. And so study up all those problems. I suggest you go through the documents I provided online, try the practice examples. If you need more practice examples, which I would recommend you do, the recommended readings are also online, some in the readings folder and some in the introduction document that I posted online before the first class. If you have any questions for me, like I said, please do email me, and I'm more than happy to get back to you as soon as I can. I'm happy to have office hours with you via Skype or some other digital means, should you wish. And yeah, Besides that, good luck, and I will see you guys later.